The other way I can arrange resistors in a circuit is to have them branching, and that would be called a parallel circuit. For a branching or parallel circuit, we have the current coming in to a branching point, and then it splits and it goes, some of it down the first branch, some of it in this case down the second branch, some of it down the third branch. And what we'll see is that the total current splits into three, and it will be then the sum of each of the branch currents. So branch 1 plus branch 2 plus branch 3 of the current will add together to give me the total current. An analogy for this would be a waterfall, where we have the water representing our current, and it comes to a place in the waterfall where it can take one of three paths. So some of the water goes down the first path, so it'd be current 1. In this case, it looks like the bulk of the water goes down the middle path, so that could be I2, and then a third amount goes down the far branch, or I3. When we get to the bottom of the waterfall, all the current rejoins and continues on down the river. So for a branching or parallel circuit, at the end of the branching, the three branches rejoin and the current comes back to one single current. In this case, with a parallel circuit, using the waterfall analogy, all the water falls the same height. So it starts here, falls here, so H is the same for each of them. As with the fountain analogy before, H is going to be equivalent to the voltage. So in each branch of a circuit that's a parallel circuit, voltage along each branch is equal. So if we look at the parallel circuit equation again, back to Ohm's law, we have the voltage equals the sum of the current in the resistors times the effective resistance. We saw that the current in the circuit is equal to the sum of each of the current in the branches. So what that tells us is the total current is equal to the total voltage divided by equivalent resistance in this case. Total voltage is the same across each branch. So for I1, we have the total voltage divided by resistor 1 plus the total voltage divided by resistor 2 plus the total voltage divided by resistor 3 that mirrors our current sum equation. So if we wanted to look at equivalent resistance in this case, we're going to look at 1 over the equivalent resistance equals the sum of 1 over each of the resistances. So that equals 1 over R1 plus 1 over R2 plus 1 over R3. When we're dealing with parallel circuits, we have to remember, first of all, that it's 1 over the equivalent resistance is equal to the sum of 1 over the resistances. And when we want to get the equivalent resistance, we have to take the inverse of the sum of 1 over the resistances. And that tends to be a step that people forget, so it's important that you keep reminding yourself about that. If we take a look at a problem, we have 3 resistors, and they're connected in series. We have a voltage of 90 volts, and we're supposed to find the current and the voltage across each resistor. First thing that I would encourage you to do is draw the schematic. So you have a power supply, resistor 1, resistor 2, resistor 3. So this is 90 volts. This one will make 10 ohms. We'll make this 15 ohms. We'll make this 20 ohms. Does the order matter? No, not at all. Since it's series, the equivalent resistance is going to equal the sum of the resistances, so 10 plus 15 plus 20. So if I wanted to put in just one resistor in this circuit, I would need a 45 ohm resistor. Since the current is constant, we know the total voltage. We now know the equivalent resistance. We can find the current. So in this case, our 90 volt power supply divided by our equivalent resistance of 45 ohms gives us the current in the circuit, and we have a 2 amp current. We want to find the voltage across each resistor. The current through each resistor is going to be the 2 amps. So for resistor 1, the voltage is going to be the 2 amp current times 10 ohm resistor, or 20 volts. For resistor 2, the voltage across it is going to be, again, the 2 amp current times the 15 ohm resistance, and we get 30 volts. Our third resistor voltage is going to be, finally again, 2 amps of current, 20 ohms of resistance, 40 volts. So if we think about it in a slightly different way, our power supply is increasing the potential energy of the charges, flows along the wire until it hits the first resistor, and then drops, flows along until it hits a second resistor, then drops, flows along until it hits the third resistor and then drops, and then makes its way back and gets pumped up again. The sum of each of the voltages should add to the voltage of our power supply. So we have 20 plus 30 is 50 plus 40. That gives us our 90 volts. So the math worked out and we got the answers that we needed to. If we take these same three resistors and we put them in a parallel circuit, again, we're looking for the current and the voltage across each resistor. Again, we start out by drawing the schematic. This time my circuit has three branches. The branches rejoin before returning to the power supply. So again, my power supply is 90 volts. We'll make this one our 10 ohm resistor. We'll make this our 15 ohm resistor. And this one our 20 ohm resistor. Again, does it matter which is which? No. In a parallel circuit, our voltage difference between this end of this branching and this end of the branching is the same as our power supply. So voltage change across each resistor is 90 volts. Our effective resistance or equivalent resistance here, we're going to do 1 over the equivalent resistance, so we're going to do 1 over 10 plus 1 over 15 plus 1 over 20. So 1 over our equivalent resistance is 0.217. Our equivalent resistance then, we take the inverse of that and we get 4.62 ohms. So if we were to take these three resistors out and put in a single resistor for this circuit, we would put in a resistor that has 4.6 ohms of resistance. So we know the voltage across each resistor. Now we can find the current. Again, using Ohm's law, voltage equals current times resistance. For resistor 1, I need to find the current through each branch this time. So current is going to be voltage, which is 90 volts, divided by the resistance, so 10 ohms for the first one. So I have 9 amps. For resistor 2, the current in that branch is going to be, again, 90 volts over 15 ohms. So I get 6 amps. For my third resistor, current is 90 volts over 20 ohms. I get 4.5 amps. Now if I wanted to find the total current in my circuit, so my total voltage is equal to my total current times my equivalent resistance. So my total current is going to be 90 volts divided by 4.62 ohms. So I end up with 19.5 amps. Now if I go back and look at the current from each of my branches, they should sum to my total current. And if I sum them, I get 19.5 amps, which is the same as my total current using equivalent resistance and total voltage. So I found the resistance, I found the current for each resistor in a parallel circuit and in a series circuit. What we're going to look at next is combinations of resistors that some are in parallel, some are in series within the same circuit.